All right, hi everybody. This is lecture 24. We're going to be discussing Stewart section 4.3, which is about the relationship between derivatives of a function and the shape of the graph of the function. I want to remind you about this Friday's quiz. This Friday's quiz will be over, there's a mistake here. This should say 4.2, 4.3, 4.4 are the three sections. At least one of the problems on the quiz will be taken right from a book example. I mean, I'll change numbers. I'm always bugging you all to read the book, and it's always a little bit disheartening how how few students seem to actually read the exposition of the book. And the thing is, I've mentioned a number of times that there's stuff that I purposely don't cover in class because it's covered well in the book, and examples that are going to be like examples that, like problems that you need to know that are done well in book examples. So you really want to study the book, and so I'm going to put some points there. At least one of the problems will be based very closely on one of the book examples. All right. Well. Today's lecture, I'm going to be relying on definitions and terminology and tests that are presented in the book, and I've also typed them up on the course webpage. So the meeting part one is about increasing and decreasing. And so the reference material again is in the book and on the web page. So I'm going to start with the definition of an increasing function. So the definition is again, it's in the book, it's also on the web page, and now you'll be referring to these definitions in recitation tomorrow. So here's the definition of a function increasing. We say a function is increasing on an interval a,b if, when you do this, when you pick x's within the interval going from left to right, so if x1 is less than x2, then the y values have the same inequality. y1 is less than y2. So for example, f of x equals x cubed. This graph looks like this. Notice if I pick any two x values going from left to right, so if I pick, say, this x value and this x value, the y value goes up from this y value to this y value. So the y values definitely go up. On the other hand, if I pick that as my x value and this point right in the middle, again, the y value went up from here to here. Or if I pick an x value that's maybe over here and an x value that's way over here, well, then the y value goes up from down here to way up here. So this function is definitely increasing, and it's increasing on the whole number line. So that is for all x in, and I don't usually use this notation, but in this situation I'm going to. On the whole number line, that function is increasing. All right. The next thing I want to introduce is what's called the first derivative test, or sorry, the increasing-decreasing test. So that's, again, in the book and on the web page. Here's the test. if f prime is known to be positive on a whole interval, then f is guaranteed to be increasing on at least that whole interval. So again, note the nouns here. F prime is the thing that's positive. F is the thing that's known to be increasing. So we're talking about two different things here. We're talking about f prime and we're talking about f. F prime is the thing that's known to be positive, and f is the thing that's known to be increasing. And similarly, if f prime is known to be negative on a whole interval, then that means this test guarantees that f is going to be decreasing on that whole interval. So observe the sign behavior of f prime of x equals f prime of x for f of x equals x cubed. So there's our f of x equals x cubed over there. F prime of x equals 3x squared. So if I think about the sign behavior of f prime, f prime of x equals 0 when x equals 0. Otherwise, f prime is going to be greater than 0. Pick any number, positive or negative, and you square it, you get a positive thing. So otherwise, so f prime of x is greater than 0 when x is not equal to 0. So we want to think about, where is f prime positive? What intervals? Well, from minus infinity to 0, not including 0, and then from 0 to infinity, not including 0. All right, well, if we apply the increasing-decreasing test, the increasing-decreasing test tells us, guarantees us, that the function f of x equals x cubed will be increasing at least on this set. So if you're not confused by this, you're not paying attention, because this is confusing. We've got this test that tells us f is increasing on this interval and this interval. This test does not tell us that it's increasing across the interval where x equals 0. But in fact, we know from the picture a while ago that we can see this function is increasing on the whole real number line. So the thing about this test, this increasing test, is this little clause that I put in, which is not in the book. The book just says, if f prime is positive on a whole open interval, then f is increasing on that interval. But the key thing is that at least needs to go in there, because it just means that you're guaranteed that much, but it might be that you get more. It might be that you have to think about how the function looks. Now, anybody remember last Wednesday's quest. Anybody got last Wednesday's notes? Yeah.
Yeah, we have to figure out how to find where the local highest values and like total highest values are, the maximums and minimums are,
Right.
without the graph.
Exactly. So given the formula for a function f, we seek, we're looking for tools, analytical tools that we can use to analyze that function that will tell us where there are maxes and mins. So we seek analytical tools that will analyze that formula and tell us where f has maxes and mins. So, and locate maxes and mins. Now, do you remember that on Wednesday I said that's a big ask? So we're not going to get like a tool that does everything. But we had a partial result, one tool that will work in some situations. What was that tool? Well, it's the closed interval method. So that's a tool that only works in some situations and only does one thing. So it can be used to find absolute mins and maxes, or absolute maxes and mins, for a function that's continuous on a closed interval. So again, as I said on Wednesday, this quest is a big ask. So there's not going to be a single tool that does everything. So this was one tool. So today we get another tool. And that tool is the first derivative test for local extrema. So notice, this test finds local extrema. All right, so here's the test. Suppose that you have a critical number of a function f. Remember what a critical number is. A critical number is an x value where f of x exists and the derivative is either equal to 0 or does not exist. And also, furthermore, suppose that the function is continuous near that x value c. So that is, there is some interval around c, so like from a to b, where on that whole interval f of x is continuous. So we've got a number x equals c that's a critical number, and it's in this interval where f is behaving nicely. Well, here's the first derivative test. If f prime changes from positive to negative at c, then at that x equals c, there's a local max of f of x. And the corresponding y value, that is, you plug c in and get a y value, that's what's called the local max value. So, and then analogously, if f prime changes from negative to positive at x equals c, then that's the location of a local min. So why does this make sense? Well, if f prime changes from positive to negative, that means that f changes from increasing to decreasing. So f was going up, and then it's coming down, and we know that there's a y value up there because the function's continuous. So this makes sense. So that's the first derivative test. All right, I want to do an extended example where we explore this. So let f of x be x to the fourth e to the minus x. So A, find the intervals where f is increasing or decreasing. All right, well, the strategy is going to be, we're going to use the increasing decreasing test. So here's the strategy. We're going to find f prime of x. We're going to analyze the sign behavior of f prime. That is, we're going to determine the sign behavior of f prime. And then once we know the sign behavior, that is, once we know where f prime is positive and negative and 0, that'll tell us where f is increasing and decreasing. So we're going to use the increasing decreasing test to determine the increasing decreasing behavior of f. All right. So again, this first derivative test is another, it's another tool in our quest. It gives us different information, and you'll see that it works in a different way. So we have our function f of x equals x to the fourth e to the minus x. So that means for f prime of x, I need to use the product rule. It turns out that I get minus 4x cubed plus x to the fourth, e to the minus x. If I use the product rule and I factor, that's what I get. Now I can write this in a couple of different ways. First of all, I can factor out an x cubed. And then I want to go one step further because I don't like factors of this form that say a number minus x. I like to have factors that say x minus a number or x plus a number. I like the x to be on the left. So I'm going to pull out a minus sign in front of the whole thing. So instead of writing minus 4 plus x, I'm going to write minus x minus 4. Oops, I'm sorry. This is a mistake. This should say here, this should say 4 minus x in this factorization. I made a mistake there. So instead of 4 minus x, I get minus x minus 4. It's the peril of skipping steps. So the factorization step leads to, let's make sure, I should have a minus 4 I made a mistake here too. This should say 4x cubed minus x to the fourth. And that is the same as this. Let's see, there's my 4x cubed, and there's my minus x to the fourth. Now let's go this way. There's my minus x to the fourth, and there's my plus 4x cubed. Good, that works. All right, now, we want to determine the sign behavior of that baby. Now, when we discussed continuity earlier in the semester, we discussed, I think, this issue that a function that's continuous can only change sign at x values where it touches the x-axis. So f prime of x is continuous. So it's continuous because it's just made up of basic functions being multiplied together, no funny stuff. There are no bad x values. And so it can only change sign at x values where it touches the x-axis. So only places where f prime equals 0 and the graph of f prime would touch the x-axis could f prime change sign. Well, so what are the x values that cause f prime to be 0? Well, the only x values that cause f prime of x to equal 0 are, drum roll please, somebody give me an x value that will cause this to be 0. Cooper's got 1.
0.
X equals 0. Cooper took the easy one. Because notice, if I use x equals 0, I get 0 cubed times 0 minus 4 times e to the 0. Well, this 0 cubed is going to kill everything. So that's definitely an x value that's going to cause f prime to be 0. Can anybody think of another one? X equals 4. Can anybody think of another one? Yeah. Negative 1, why?
You did the negative 1 power, you did the first power 0 correctly.
Say it all again.
You plug in negative 1, you end up in the end with e to the first power, and I believe e to the first is 0, if I recall correctly. I could be remembering that wrong.
it might be e to the 0 is 1.
Yeah, e to the 1 is 0. What's the range of the e to the x graph? You're trying out for the cheering squad, and you have to do the hand motions for the e to the x graph. So who can do this hand motion? Is it the field goal sign? No, that's x cubed, x squared. What are the hand motions for e to the x? Stand up and demonstrate this. We need the camera to go over there. There we go. So there's the graph of e to the x. Thank you. You're on the squad. This is y equals e to the x. And so we see that e to anything is always greater than 0. It's never equal to 0. So in fact, this term is never 0. So the only things that are going to cause f prime to be 0 are those two x values. So we make a sign chart for f prime. I'm going to do this over here. Now remember, f prime of x we decided is, or I decided, I did all the work, I'm taking all the credit, minus x cubed times x minus 4 times e to the minus x. So we've got 4 things going on here. A minus, we've got an x cubed, we've got this factor, and we've got e to the minus x, and we've got 2 important x values. Well, I make a sign chart by making a column for the x values. And let's see, my important x values are going to be certainly x equals 0. I'm going to put that in the second row. In the first row, I'm going to have x's that are less than 0. And then I'm going to skip a row, and I'm going to have x equals 4 on the 4th row. In between those, on the 3rd row, I'm going to have x's that are greater than 0 and less than 4. And then the last row is going to be x's that are greater than 4, or I'm going to say 4 is less than x. My style is I like to have all my equal signs going this way, if possible, or my inequalities going that way. So those are the x values where I need to figure out the sign behavior. Because remember what I said a while ago, f prime is a continuous function. The only way that it can change sign from positive to negative or negative to positive is by crossing the x-axis. And that only happens at these places. All right, so what we're going to do is we're going to analyze each of these factors by itself. So first of all, I'm going to have a column for the minus sign. I'm going to have a column for x cubed. I'm going to have a column for x minus 4. And I'm going to have a column for e to the minus x. And then I'm going to have a column for f prime, which is the product of all those things. Okay, this column's easy. There's a minus sign out front. It's always minus. It's just chilling out front. So minus, 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 minus. And we've just discussed this column. E to anything is always positive, greater than 0. So there's pluses in all of these cells. But what about these factors? The x value that causes that to be 0, that was Cooper's idea, when x equals 0, that causes x cubed to be 0. Now let's think about all those other x values. Any x value that's greater than 0. Well, I don't have to go through all of them. I just pick any of them. Like say x equals 4. X cubed would be 64. So that means positive. But it's the function is never going to touch the x-axis again, so all of these are positive. So this factor changes, well, think about a negative x value, like for instance, x equals minus 4. Minus 4 cubed would be minus 64. That's negative. So this factor changes from negative to 0 to positive at x equals 4. Now think about this factor. The x value that causes this factor to be 0 is the number 4. So there's a 0 in that cell. And if I pick any number that's greater than 4, then x minus 4 is going to be greater than 0, so there are going to be positives here. If I pick any x value that's less than 4 and I subtract 4 from it, I'm going to get something that's negative. So this factor changes from negative to 0 to positive at x equals 4. Now let's think about the product of all these things. A minus times a minus times a minus times a plus is minus. A minus times a 0 times a minus times a plus is 0. A minus times a plus times a minus times a plus. Again, these factors are all just being multiplied together. I get a plus, I get a 0, I get a minus, and that's the end. Actually, And look, we can actually have a column for f. I can tack that on. If f prime is known to be negative on that whole interval, then f is decreasing. And if f prime is known to be positive on that whole interval, then f is increasing. And if f prime is known to be negative on this whole interval, then f is decreasing. And here we know that there's a horizontal tangent and a horizontal tangent. So our question, though, was to find the intervals where f is increasing or f is decreasing. So I want to write the conclusion, and I want you to pay attention to the precision that you need to use when you describe this kind of thing. The conclusion is f is increasing on the interval 0 to 4, and that's because f prime is positive there. And f is decreasing on, well, negative infinity to 0, not including 0, and also 4 to infinity, and that's because f prime is negative. I wanted to write these out because, for one thing, I think it's important to write these out and also pay attention to pronouns, and actually that I don't use pronouns. A common thing that students will say is something like, it's increasing because it's positive. So if you think about that from a standpoint of English grammar, if you say it's increasing because it's positive, it is referring to something, to just one thing. That sentence is actually false. It's completely wacky. To say something is increasing because it's positive, that's confusing the idea of increasing and the idea of being positive. Increasing means the graph looks like it's going up. Positive means the graph is above the x-axis. Two different things. So to say that something is increasing because it's positive is nonsense. Knowing that something is increasing knowing that something is positive doesn't tell you anything about whether that thing is increasing or decreasing. What we have in this situation is we have one function, f prime, that's the negative thing, and then a different function that is f, that's the decreasing thing. So again, you don't say it's decreasing because it's negative, because that's nonsense. You say f is decreasing because f prime is negative. So you want to always say all those words to keep in your head the distinction between increasing and positive and the distinction between decreasing and negative. They mean different things. All right, question B. Find the local max and min values. Okay, our strategy will be we're going to use the first derivative test. So let's go back and put the first derivative test back up. It says that if f prime changes from positive to negative at some x value, then there's a local max there. If f prime changes from negative to positive, then there's a local min there. So if you look at our chart over there, you can see at x equals 4, here, f prime changes from positive to negative. So that tells us that f has a local max. So, and as always, I like to say y, write a conclusion that says y. F has a local max at x equals 4, and that's because f prime goes positive to 0 to negative. According to the first derivative test, if f prime does that, then f has a local max. The local max value is f of 4. That's, for that I go back to the original function. That's going to be x to the, it's going to be 4 to the 4th times e to the minus 4. So that's going to be 256 over e to the 4th. Okay, f has a local min at x equals 0, because if you go over to this table, at x equals 0, f prime changes from negative to 0 to positive. That means f changes from decreasing, going down, to increasing, going up. So f has a local min at x equals 0. I'm gonna move this up to the top of the board so those of you who are farther back can see it. F has local min at x equals 0 because f goes negative to 0 to positive. And then x equals 0 is the location, but we need to compute the y value, the local min value. Is the y values. Here I should have said y equals. The local min value is a y value, so f of 0. So that's going to be, we go get the original function, 0 to the 4th times e to the minus 0. So that's 0 to the, so that's 0 over e to the 0. So that's 0 over 1. So that's the number 0. So here's a graph of the function. Notice at x equals 0, there's a local min. The y coordinate is y equals 0. At x equals 4, there's a local max. The y coordinate is 256 over e to the 4th, which is about 4.7 or so. All right. So that's meeting part 1, which is increasing, decreasing. Meeting part 2 is concavity. So I'm going to start with a definition of concavity. So a function is said to be concave up on an interval if the graph lies above all of its tangent lines on that interval. So here's a picture of a graph that does that. Let's think about a tangent line on this graph, like that one. Now, when I say that the graph lies above its tangent line, that might sound a little weird, because you can see here the graph is way down here, and over here this tangent line is way up there. But the idea is, if you pick any x value and take a slice at that x value, that graph is above that orange tangent line. So I would say that this is concave up, and here's the symbol for it. It's like a bowl that holds water. Concave down, of course, would be the graph is below its tangent lines. And there's a symbol for this. Also, you can do that, like a bowl that's upside down. Now, what's called an inflection point is a point on the graph where the function is continuous and the concavity changes from up to down or down to up. Now think about that. Concavity is discussed in terms of the graph being above its tangent lines or being below its tangent lines. So a point of inflection is going to be a place where the graph actually crosses its tangent line. So an inflection point could be something like this. Here's a graph that's concave up, and here the graph is concave down. So here it's pretty clearly concave down. Here it's pretty clearly concave up. If you think about the tangent lines, the graph is staying above the tangent line. Now, dang it, I hate when I break my precious orange chalk. Now, don't be duped by the fact that this tangent line, if I continued it way over here, would cross the graph. What I'm interested in is what's happening near the point of tangency. Near the point of tangency, the graph is staying above that tangent line. Now think about this tangent line over here. Near its point of tangency, the graph is staying below its tangent line. And similarly for all those x values nearby. So that's why this chunk of the graph is concave up, this chunk of the graph is concave down. Now think about what happens like at this point right here. If I draw the tangent line and I zoom in, graph actually crosses, I didn't draw this very well, but the graph crosses that tangent line right there at that point, not somewhere off in the distance. Okay, now, so that's the definition of concavity, and then we have what's called the concavity test. It's analogous to the increasing-decreasing test, but it's about f double prime. If you check the sign behavior of f double prime and find out that f double prime is positive, that on an interval, that tells you that the function f is concave up on that whole interval, at least. And if f double prime is known to be negative on some whole interval, that tells you that f is negative on that whole, f is concave down on that whole interval. All right, well, we're going to return to that monster example that we did a while ago Now remember, for this function, f of x was equal to x to the fourth e to the minus x, and we figured out that f prime of x equals four x cubed minus x to the fourth e to the minus x. And we figured out that that was, after I factor it, it's minus x cubed x minus 4 e to the minus x. So that's the function we're dealing with. So C, find the intervals where f is concave up or concave down. All right. Well, the last one, well, for one thing, I kind of crashed and burned because I tried to not show the details, but I want to try to not crash and burn. So the strategy is we're going to find f double prime, we're going to analyze the sign behavior of f double prime, and we're going to use that concavity test to tell us about the concavity behavior of f. So find f double prime, determine the sign behavior of f double prime, and then use the concavity test. Okay, well, the solution is f double prime of x, that's going to be the derivative of that thing, 4x cubed minus x to the fourth e to the minus x. When you go through all the steps with the product rule, you get kind of a mess. You get x to the fourth minus 8x cubed plus 12x. 12x squared e to the minus x. And that factors as x squared, x minus 2, x minus 6 e to the minus x. Now I'm not going to draw the whole table, but I'm going to draw the first and last columns. So here's a sign chart for f double prime of x, and I'm going to write it out here again. X squared, x minus 2, x minus 6. E to the minus x. Now notice we can expect that there are 3 x values where f double prime is going to be 0. So the x values where f double prime is 0 are x equals 0, and x equals 2, and x equals 6. Because that causes that factor to be 0, which kills the whole thing. This causes the second factor to be 0. This causes the third factor to be 0. So we need to investigate these intervals. X less than 2, x less than 0, x between 0 and 2, x between 2 and 6, and then x greater than 6. It turns out that when I do this, I get this behavior. Plus 0, minus 0, plus. What's interesting here is that the signs don't keep alternating. F double prime changes from positive to 0 and then back to positive. And that's because this factor changes from positive to 0 to being back to positive. It doesn't change sign because it's x squared. Okay, so that tells us that F is concave up, concave down, and concave up. So our conclusion is F is concave up on, let's see, minus infinity to 0 and 0 to 2 and 6 to infinity. And that's because F double prime is positive. And we see that F is concave down on the interval from 2 to 6. And that's because F double prime is negative. All right, so question D is find the inflection points. So the inflection points in F are going to be the x values where the concavity changes. So at x equals 2, because F changes concavity from down to from up to down, and at x equals 6, because F changes from concave down to concave up. So the y coordinates are well, the first one is going to be y equals f of 2. So I go back to my original function. 2 to the 4th, e to the minus 2. So that's going to be 16 over e squared. And the other one is y equals f of 6. So that's going to be 2 to the 6th, e to the minus 6. So that's 1028 over e to the 6th. So my inflection points are x equals 2, so xy equals 2 comma that y value, 16 over e squared, and xy equals 6 comma that y value, 1028 over e to the 6th. We can get those on the graph. So I can add 2 comma f of 2 and 6 comma f of 6. I'm going to move this point up higher. So notice the graph is concave up, then concave down, then concave up. So that's those are those two inflection points. Now look over here. Remember I said the concavity test tells us that the function is concave up from negative infinity to 0, and then again from 0 to 2, at least. But in fact, we can see that the function is concave up on this whole interval. So actually, we can do better. So f is concave up on actually from minus infinity to 2. Even though the concavity test didn't tell us that, here the second derivative was not positive. The second derivative was 0. But the function was concave up there, it's concave up here. And if you think about concavity in terms of tangent lines, any tangent line I put on the graph in this whole interval, the function stays above that tangent line. All right, sorry I kept you a minute late. If you didn't sign in yet, be sure to find the sign-in sheet to sign in. Gabriel will see you tomorrow in recitation. The recitation tomorrow is only, I think, 4 problems, so it's not quite so crazy.